All right, welcome back everyone. In this video, we'll be looking at a solution to the exercise of creating a DFA M that accepts the language L, where L is the set of all strings over the alphabet 0, 1, such that the strings do not contain 0, 1 as a substring. So in other words, L is actually, so this string L, let's call it L1, right? L1 is actually the complement, right, of W contains substring. So if, let's say, this was L2, then L1 is actually the complement of L2. And so actually I'm going to use this to my advantage, and I'm going to use this to introduce a property of DFAs. So there's a property of DFAs. So suppose you have a DFA M, which let's say is written as Q over the alphabet sigma, using the transition function delta, starting at Q0 with final states F, right? So you have some machine, right, with some final states, okay? Right, and so this machine, the language accepted by this machine is L1, right? Then, if you create a DFA M prime, right, which is the same states, same alphabet, same transition function, same initial state, but the only thing that you've changed is F prime, right? You change the set of final states, right, where the set of final states is now the set of states from your DFA, your initial DFA, this DFA here, right, different the set of final states in your DFA M, right? So in other words, what's going on is if you have a DFA, let's actually draw at the same place here. If you have a DFA like this, you know, you have some transitions, something like this, right? So this is M. Then what M prime is going to look like is every final state is going to become a non-final state, and every non-final state is going to become a final state. So then that would look something like this is final, this is final, this is final. Whoops. This is final. Then these two guys are no longer final states, right? So this machine M prime, right, the property is that the language accepted by M prime is actually going to be the complement of the language accepted by M, right? And so I'm going to actually omit the proof, right? But I encourage you to try to work out the proof. And in fact, it's actually quite simple. So I really highly encourage you to try to work out the proof. But in this case, I'll omit it, okay? I'll omit it, but I'll be using this property to my advantage to solve this question, right? Because I actually know how to create the DFA that accepts all strings that contain 0, 1 as a substring, right? That's actually quite easy to create, right? So, whoops. So, let's add a page. So that machine, right? The machine, right, the DFA for L2 is quite simple, right? It's just if you have a 0 and then a 1, right? So if you see a 0 and then a 1, then accept, right? And then you just fill in all the remaining transitions, right? So this is the trick of creating the sort of bare bones of your machine, right? So creating the bare bones of your machine, bare bones of your machine, hard coding, essentially hard coding the shortest string. And then 2, just completing the transitions. Because it's a DFA, you know that each state will have one transition for each letter in your alphabet, or each symbol in your alphabet, right? So in this machine here, if I'm in my start state and I see a 1, well, in that case, I'm just going to wait for 0, 1, right? So I'm just going to be waiting for 0, 1, right? So here I'm waiting to see 0, to see a 0. Then once I see a 0, right? Once I see a 0, then I'm just waiting to see a 1, right? Because as soon as I see a 1, that means I've seen 0 and then 1, right? So then in this case, if I've seen maybe some 1s, then a 0, and I see a 0 in this state here, then I'm just waiting, right? I'm just in limbo. I'm just waiting for that 1 so I can quickly go to the accept state, right? So that means that here, in this state, what I'm doing, this state here, so I know that I've seen a 1, I've seen a 0. I'm now waiting to see a 1, okay? And once I do that, right, so once I'm here, right, I know that I've seen 0, 1, so I accept everything else. Right? I know that my string has the property that I wanted, and so I don't care about its other characteristics, its personality, and any other case. I accept it, right? I just accept the other components, the other personalities of my string, right? And so that just means that once I'm in an accept state, once I'm in this accept state, I just stay there, okay? So that's the machine, or the DFA for L2, right? So this was L2. What I actually care about is creating the machine for L1, but I know that L1 is the complement of L2. So all that I need to do is, if this is my machine M, then I can create the machine M prime by making the accept states non-accept states and the non-accept states accept states, right? So in this case, that looks like this becomes an accept state, this becomes an accept state, but then this doesn't, right? And so now M prime is going to be the machine that accepts L1. And you can clearly see this, right? So imagine you have, let's say, 1, 0, 0, right? So if you have 1, 0, 0, 0, 1 isn't in here, right? So you should be accepting that. Well, let's see. So 1, 0, 0. So that's good, right? But as soon as you put a 1 in front, right? Or at the end, sorry. As soon as you put a 1 at the end of the string, then you have a 0, 1. And so that's going to be a reject. And so then you can't recover, right? You can't undo the sort of crime that you just committed of introducing a 0, 1 into your string. And so you're going to keep rejecting, okay? And so I've essentially used this exercise to introduce this property of DFAs, which is a quite nice property. And again, I highly encourage you to try to come up with a proof, okay? All right, so that does it for the solution video for this exercise.